All right, so why do different things dissolve differently, and why is there sometimes a sort of a limit to how much can be dissolved? Well, probably the most important factor for understanding why things dissolve in each other is intermolecular attractions. And so the saying like likes like, meaning if you're polar, you like other polar compounds. Also ionic. If you're polar, that means you've got sort of positive negative charge. So you can also be attracted to polar compounds. So to ionic compounds. So that's why lots of salts will dissolve in water, because water is very polar. So likes means that polar or ionic compounds will dissolve in other polar substances. So polar solvents will dissolve polar or ionic solutes. Nonpolar solvents will dissolve nonpolar solutes. So, we talked about oil and water not mixing. Oil is nonpolar, water is polar, so they're not going to mix. Salt is ionic, and it will mix with water, which is polar. Alcohol is also polar, and water is polar, so that's why they mix so well with each other. So intermolecular attractions are super important. And then the other factor is that there's a tendency toward disorder. So if it turns out that the two different compounds are very similar in the type of attractions they have, then they're just going to mix because there's a tendency toward order. They're just going to start mixing up, and that's why we get a solution. So random motion will lead to diffusion, which is a type of disorder. So, like I said, polar molecules will react with polar solvents. So in this case, a polar solute like alcohol has a positive end and a negative end. Water has a positive end and a negative end. And so you can see that they're attracted to each other. So the positive end of the polar solute will be attracted to the negative end of water, and the negative end of the polar solvent will be attracted to the positive end of water, and so they can mix. Because the solute and the solvent have very similar attractions to each other and to the other one, they're all very similar. That's when randomness takes over, and so they don't care who they're attracted to. They're just attracted to they're all attracted to each other, and so they will just naturally move around, and the disorder takes over, and they don't care who they're attracted to. kind of a I don't know, like a, what do you call that, an orgy or something like that. Anyway, obviously they don't have feelings. So polar solvents and polar solutes are attracted to each other, and because they're similar attractions, disorder takes over, and they don't mind who they're attracted to, and so they mix up evenly. So if you take vinegar, which is polar, and you mix it with water, you can get salad dressing. Now, when you throw oil in there, it doesn't mix. That's a whole nother thing. But vinegar will dissolve in water. Alcohol will dissolve in water. Very similar. Okay, and then in the same way, nonpolar solutes will interact with nonpolar solvents. Again, neither of them have strong attraction, so neither of them are polar. So the solute is sort of very loosely attracted to itself, and the solvent is very loosely attracted to itself, because they all have London dispersion forces. And again, because the interactions between the solvent and solute are very similar to just solvent or solute, because all the interactions are similar, disorder takes over and everything will mix really well. And so nonpolar will interact or dissolve in nonpolar. So example of that, gasoline is actually made up of a lot of different nonpolar compounds, like heptane, octane. There's lots of different ones. Benzene, they all mix together really well because they're all nonpolar. Okay, so polar solutes will not dissolve in non-polar solvents and vice versa. And the idea is the same. So we'll just stick with this. So polar solute, non-polar solvent. It could be non-polar solute and polar solvent. It would be the same idea. So if you've got your polar solute, there's really strong attractions between all the solute molecules. The solvent is nonpolar, so there's weak forces between the nonpolar solvent molecules, but those nonpolar solvent molecules don't have a strong enough attraction to pull the polar solute molecules apart from each other. So they stay in their own lane, so to speak, because too much energy is needed to break the polar interactions to try to get them to mix. So disorder doesn't really take over because the two different attractions are very different. The polar interactions are very strong and the nonpolar are very weak, and the nonpolar ones can't get in to break up the polar. So water has very strong hydrogen bonds, very polar, and gasoline or oil or those kind of things have very weak London forces, and so those London forces are not strong enough to get in and break the water molecules apart, and so they stay in their own little section. So yeah, gasoline and water don't mix, oil and water don't mix. So this picture sort of shows you. So if there's really strong attractions here between the polar solvent in this case, A and B are A is the solvent, and you can see the arrows are showing sort of a strong attraction between A, and then B is the nonpolar solute in this case, and these attractions are weaker, and you can see that the interaction between B and A is so much weaker than the interaction between A and A. This is much weaker, that these can't get in and break them apart. And so there's an overall pull on this molecule in this direction, which means that the polar solvent will stay by itself and the nonpolar solute will stay by itself. So that's like the oil and water. And it's so strong that it can't be overcome by random mixing. Just sort of an example, I talked earlier about oil and vinegar. If you've ever tried to mix them, you know that you can mix them sort of temporarily, but they never quite look mixed. You get like little globs of oil and little globs of vinegar, and they never quite mix. You can get them mixed enough to pour them on something, but then they're going to separate out right away. When you're mixing it, that's not considered a solution. That's considered, well, it's kind of a suspension, like I said earlier, a suspension. So you can kind of get them all sort of mixed up, but they don't stay that way. Okay, and then finally, what about ions? We know that polar solvents have a positive and negative end to them, and so they also react really well with solutes that are ionic. So you can see here, and this is what happens. I think there's a video later. So let's say this is sodium from salt, and this is chloride. The sodium ions are attracted by the negative ends of water, and in fact, you might get a few more sort of surrounding them. All the water molecules will surround the sodium ion, so the negative ends, and then all the positive ends of water will surround the negative ion. So one end will get the O's and one end will get the H's. And so we can, and we'll look at this in just a minute, we can often dissolve ions. Okay, so again, the positive end of water is attracted to the negative anion, and the negative end of water is attracted to the positive cation. So what happens, you see, here's your solid salt. In this case, it's potassium chloride, but it could be sodium chloride. It could be any salt that's soluble. So what happens is you can see here that the water starts to attract to the solid salt. The the positive ends are attracted to the chlorine when enough, or here, you can sort of see it here, and the negative ends of water are attracted to the positive ion. So when enough water molecules surround an ion, it actually can pull it away, and it pulls it away, and like here, it surrounds the ion. In the same way, the positive ends of water will come. So this chlorine was probably attached to this potassium earlier, and so the water has come and surrounded the chlorine and pulled it out. And so one by one, each little ion is pulled. This is called the dissolution process, or sometimes it's called hydration, because you're dissolving it in water. Sometimes it's called solvation because it's being dissolved in the solvent. Hydration would just be that water is the solvent. So anyway, this little video, again, I can't show you right now, but you can click on it if you go to the PowerPoints, or you can just type in water dissolving or salt dissolving in water, and you can see this little molecules. You can see that this actually happens over time, that the water molecules come in, surround an ion, and drag it away, and eventually they all get broken apart because of those strong attractions with water. What's happening is the pull on the ions is strong enough to break the lattice energy, which is the energy holding the ions together. So we already know from earlier chapters that some solids are, some ionic solvents are very soluble, and others are not very soluble. We had our table of used our solubility rules. We know things like sodium, anything with sodium, potassium, nitrate, any of those tend to be very soluble. Whereas, remember, our lead or our silver, things like that, were not soluble in water. And that all has to do with this balance of energy. So the energy of hydration is how easily water is attracted to the ion, how much can it pull on the ion. And then the lattice energy is the energy that's holding the ions together. So if the hydration energy is greater than the lattice energy, then that means that the water ion bonds are stronger, and they can break the bonds between the ions. And if the hydration energy is not strong enough to break those bonds, then the solid will stay dissolved. It's not soluble. And there's a lot of things that can affect that, and you may not have noticed at the time, but when we do our solubility rules, the sodium, the potassium, the lithium, all those group 1A salts are always soluble, and that's because they have a low charge. So the bigger the charge is, so like magnesium and oxygen will have a much stronger lattice energy because they're both +2 and -2. They're held on to each other tighter, much harder for the water to get in there and pull them apart. And so we're not going to get too detailed in this, but just realize that some salts can dissolve easily because the water is strong enough to pull them apart from each other, whereas other salts are not soluble because, again, the strength between the two ions is so strong that the water can't get in there and pull them apart. Okay, so here's what I was talking about. Lattice energies will depend on two factors. So what makes those ions really attracted to each other? The first thing, like I was just saying, is the charge of the ion. So the greater the magnitude of the charge, the stronger the lattice energy. So like I was saying, if you have your +1 or -1 charges tend to be weaker than +2 or +3 or -2, -3. So all of our salts with ions like potassium, sodium, chloride, nitrate, those all tend to be more soluble because the lattice energy is weaker. The sulfates and the phosphates tend to be stronger lattice energies, and so they tend to be less soluble. So charge of the ion is one thing, and then also the distance between the ions can make a difference. So if you have really small ions, they can get closer together, which means the lattice energy is stronger, they're more attracted to each other, and harder to pull apart. So like lithium chloride would be less soluble than sodium chloride because lithium is smaller than sodium. So smaller ions tend to be less soluble in general. Now it's all a range, so it's hard to know for sure. And like I said, there's some exceptions to the rule, like silver is a +1 ion, but it's still very insoluble. So this is just a general rule to keep in mind, and we won't get too detailed. Okay, so when we dissolve salts, or not just salts, but when we dissolve, well, mostly salts, but other things too. When we dissolve one thing in another, oftentimes there's heat involved. Heat is either evolved or absorbed when something's dissolved in water. This heat of solution can be quite noticeable. Sometimes if you put sodium hydroxide in water, it gets really, really hot. If I make that solution sometime, I'll show you in lab what I just said. Ammonium nitrate actually dissolves in water and gets colder. This solution is endothermic, so it actually pulls the heat out of the liquid and makes it even colder. That's what hand warmers produce heat when the sodium acetate in a supersaturated solution precipitates. So actually the solid is coming out of water, so it's exothermic. So it comes out of solution and it absorbs the heat from the water and cools it down. So let's talk about the effect of temperature and pressure on solubility. We kind of touched on this earlier, but let's start with gases. The solubility of solutes we know is very temperature dependent. If you heat it up, if you have soda cold, it's very, very bubbly. It's got a lot of gas in it. If you heated it up, all the CO2 would be driven out and it would be very flat. So if you get warm soda, it's much flatter. So for gases dissolved in liquids, as temperature increases, generally solubility decreases. So there's this first picture over here on the left. You can see that this is solubility. It's not telling you in what, but I'm assuming, I don't know what it's soluble in, because some of these are not soluble in water. But anyway, it's just showing the solubility of CH4 decreases with temperature, the solubility of O2 decreases, and you can see all of them decrease. That's one of the problems with global warming is if the Earth gets warmer, less oxygen can be dissolved in water. So all of our aquatic creatures will not have as much oxygen because the solubility of O2 will decrease with increasing temperatures. Now the other thing is for solids, most solids will dissolve in liquid and solubility increases with temperature. So if you think about your sweet tea, you know, if you have iced tea and it's unsweet and you're trying to put sugar in it, you're not going to ever get it to where you want it. The sugar will never dissolve in your cold water. However, if you make hot tea, you can put lots of sugar in it, make it as sweet as you want, and then if you really want it iced, then you can cool it down. So it's more soluble in the increased temperature. So you can see on this is just solubility for various salts, and it's not like hard and fast. Some of them are different. So in fact, this blue one, cesium sulfate, actually gets less soluble as you increase the temperature. For most of them, this green line is barium nitrate. This dark blue line, sodium sulfate. It gets to a certain temperature and then it'll stop. But what is this one? Sodium Na2HASO4. Anyway, it gets more and more soluble. Pressure changes depend only on, they can affect the solubility, but really they only affect the solubility of gases. So if you increase the pressure, generally you're not going to change the solubility of solids in a liquid. However, it will affect the solubility of gases. So pressure changes. So this is called Henry's law. So you can see here on the first side, if it's at low pressure, so meaning that there's fewer molecules in the vapor above the liquid, then the solubility of that gas is low. But if you increase the pressure, so now the pressure in this one over here is much greater, and you can see that more of the gas is dissolved in the water. So if you increase pressure, you increase solubility. It's because for a gas molecule to dissolve, it has to first collide with the surface. So if you increase the pressure, the number of collisions will be greater, and so more of them will end up in the solvent. Sorry. This is, like I said, is Henry's law. It says the solubility of a gas in a liquid is directly proportional to the partial pressure of that gas in direct contact with the liquid. So the higher the pressure, low pressure here, lower solubility, high pressure here, higher solubility. This is the equation that that holds. This C is just concentration. The concentration is directly related to the pressure, and KH is just called Henry's law constant. So that will depend on the solvent, and so that would be a constant would be given to you. So the pressure is directly related to the concentration. Some examples of that. Okay, so yeah, C is the solubility of the gas, the concentration, and KH is the Henry's law constant. So here's some examples of Henry's law. If you are scuba diving and you come up too fast, what's happening is when you go further down in the ocean, you're under higher and higher pressure. So more of the gas that you breathe in will dissolve in your bloodstream or in the liquids in your cells, and so you will dissolve more gas. If you come up quickly, the gas will come out of solution very quickly, and that's what the bends are that give you, really bad cramps, because the gas has nowhere to go. If you come up very slowly, it will equilibrate, and you can get the gas out of your bloodstream slower, and so that's why scuba divers have to come up slower. And again, it's because the deeper you go underwater, the higher the pressure on you, the higher the gas pressure is, and so more will dissolve. So a slow return to normal pressure can help you equilibrate or gradually. Another example is a hyperbaric chamber. I think for burn patients, but also for carbon monoxide poisoning, and actually interesting for scuba divers that get the bends. A friend of mine had the bends and had to be in a hyperbaric chamber. A hyperbaric chamber, they again increase the pressure inside the chamber to 1.5 to 3 times normal atmospheric pressure, and so again more of the gas will dissolve in your bloodstream and in the liquid in your cells. And so I had an aunt actually who got treated in a hyperbaric chamber because she had a scar that they were trying to get it to heal, and so they wanted to get more oxygen in there. Or burn victims, same thing, they're trying to get more oxygen to increase healing. And so it's also used for carbon monoxide poisoning because they're trying to increase the amount of oxygen inside the blood or inside the fluids in your body. Champagne, one other example of Henry's law. When champagne has an extra step, so when you have grapes and they ferment, the yeast will turn into glucose from the grape, so it'll turn glucose into carbon dioxide and ethanol. So that's where the alcohol comes from. When you're fermenting sugar, you're getting ethanol, and carbon dioxide is the byproduct. So if you're just making wine, normally that CO2 is released by valves, and and so the CO2 is released. But for champagne, they actually get to some point where they actually add a little bit more sugar before the bottle is sealed, and then so they capture the CO2 and it becomes trapped in the bottle. The CO2, as long as the CO2 is in there and high, the CO2 will stay dissolved, but once you open the bottle, the pressure of the CO2 in the atmosphere is much lower than what it is in the bottle, and so the CO2 is released, and that's where all the bubbles come from. Same thing with your soda. Your soda is packed under high concentration and it's sealed, so your soda inside has a lot of gas in there because it has a high solubility because the pressure is high. And then once you open it to atmospheric pressure, the CO2 in the atmosphere is much lower than it is in the bottle, and so that the gas cannot stay dissolved anymore, and it has to come out. So again, that's Henry's law.